Good evening, everybody, and welcome back if you've been with us before. This is Seth McGowan, Vice President of the Adirondack Sky Center and Observatory, and I'll be your host this evening. The Adirondack Sky Center and Observatory is proud to present now the fourth presentation in our Cygnus series. This is intended to be interactive, virtual, live, and educational, and takes place each Friday at 7 o'clock through Columbus Day weekend. We've developed this series as a way of bridging our educational mission during this period of social distancing and limited gatherings. And we hope to see you soon again. Until then, please register each week for a new and exciting program. We'll talk more about that at the end of the show. I am actually broadcasting from high atop the Astro Science Center. If you can see my screen here, this is the proposed Astro Science Center with a planetarium built in there and a research grade telescope over in this direction. If you know, our roll-off roof observatory is over in this direction here, so that's our plan. But we are about to launch our live virtual and interactive stargazing this week, actually. We're going to experiment one last time tomorrow, and then we'll be in touch with some to be part of a beta test. So look for that advertisement to come out pretty soon. For anybody who's new to the Adirondack Sky Center and Observatory, you'll notice our location is great for astronomy. We've got class 4 Bortle skies, and that's not all. Our Astro Science Center is currently under development and will become a reality and an important destination for all ages. Our numerous interactive exhibits are being developed currently and will educate and thrill our visitors as we Earth-bound creatures continue our exploration into space. In addition to the exhibit hall and continuing our hands-on approach to astronomy is our makerspace hands-on classroom, where visitors will be able to engage in virtual reality, telescope making, and much, much more. Our lecture hall will be a great place for larger groups to hear about the wonders of space, and our premier planetarium will take you on trips beyond your wildest imagination. We invite you to be part of this exciting future by becoming a member of the Adirondack Sky Center and consider a gift to help make the Astro Science Center a reality. We are currently in capital campaign mode, so we are also seeking larger, generous donations. If you're interested in doing that, please give me a call. I'll provide you with my contact information at the end of tonight's presentation. So again, capital campaign underway, about a $15+ million project to build the Astro Science Center. And we really want to make that happen sooner. We're hoping in time for the next eclipse, which will be in totality right here in Tupper Lake. So we're excited about that. And now on with the show. Before we begin, you'll notice that your mics are, of course, muted to ensure that everybody can enjoy the show without extraneous sounds. Please feel free to use the chat feature to ask questions during the lecture. If your question is not answered during the presentation, of course, a Q&A period will take place immediately following, where you'll have the opportunity to unmute and ask your question directly to tonight's speaker. Tonight's presentation, as well as all of our talks, are available the following day on our YouTube channel. You'll have a link for that at the end of tonight's presentation as well. So now it's my pleasure to introduce Mike Adler, straight from Jackson Hole, Wyoming, and Vice President of Wyoming Stargazing, where they come for his telescope and stay for his images. Tonight's presentation, Jupiter Rediscovered. Mike, take it away.
Okay, thank you, Seth. All right, I'm going to get my presentation up, and here it is. So this is, as Seth just said, the title is Jupiter Rediscovered, and what I mean by that is it's being there's a satellite up there called the Juno satellite that's currently orbiting Jupiter, and we're learning amazing new things about Jupiter on the basis of that. There's been several other, the Galileo satellite was the precursor to that, and then there were earlier satellites that also provided some knowledge about Jupiter, but the Juno is, as I'll get into this, is allowing us to learn a tremendous amount more. I'll talk about these pictures in a bit. This was a picture that I made from raw images from the Juno spacecraft, and I'll talk about that in a bit. Let's see, I've got to be able to, all right. So what we're going to do today, we'll talk a little bit about the Juno mission, the internal structure of the planet, belts and zones in the planet that everybody's pretty familiar with, and then get into some of the scientific results from the Juno satellite, the gravitational fields, what's going on at the polar regions. The Juno satellite, well, I'll get into that, and then also the magnetic field, which is also a major goal. So just to bring people up to speed on Jupiter itself, Jupiter is, needless to say, it's our largest, the largest planet in the solar system. It's so big that it weighs 2.5 times of all the weight of every other planets put together. It's about 89,000 miles in diameter, which is about 11 times the size of the Earth. Its axis is almost perfectly upright, and like the Earth, which has a 23-degree axial tilt, Jupiter is just about 3 degrees. And moving on to the next slide, we'll talk a little bit more about that. The distance between the Sun and Jupiter is about 490 million miles, which is about 5 times the distance between the Earth and the Sun. Jupiter has an unusual, well, and Saturn have an unusual relationship. Their orbits. Yeah, someone is unmuted, but anyway. Jupiter and Saturn are in a 5-to-2 resonance. So Jupiter's orbit around the Sun is 12 years. Saturn is 30.
I mean, from the...
Yeah, and I'm trying to get the screen up.
Yeah. Okay, well, and it's a resonance. And so for every 5 times that Jupiter goes around the Sun, it's lined up with Saturn twice. The temperature of the outer layers of Jupiter, the clouds, are quite chilly, 234 degrees Fahrenheit, give or take. But the core is estimated to be about 43,000 degrees Fahrenheit. The other factor about Jupiter, it has a 10-hour rotation period, which is the fastest rotation of any of the planets. We now get into a little discussion about the Juno. So Juno was launched in 2011 in August. It did a flyby around Earth, and after maneuvering, it entered the Jupiter orbit on July 5th of 2016. This is what the satellite looks like. It's a little unusual for being out there that far from the Sun. It is solar powered, and the Galileo was had a nuclear power to it. You can see it roughly what its size is. The center part where the instruments are is about 11 feet in diameter. The spacecraft has quite an array of scientific instruments. It's meant to be able to measure the gravity of the satellite of Jupiter, and I'll talk a little about that. It has a microwave radiometer that operates on 5 different frequencies and allows it to probe the depths of Jupiter at different frequencies, meaning different depths. It can measure electric fields, plasma waves, and particles. It also has an ultraviolet and infrared camera, and it also has what's called the Juno cam, which it almost seems like an afterthought, because if you look here, Juno cam is sitting, okay, here it is. It's a tiny little thing. It's right up there. It is a little camera, probably about a foot, less than a foot in size, in square or cube. It's only 2,000 pixels size. It has a sophisticated, one aspect of it that is sophisticated, because the satellite is rotating, and so there's a mechanism on that to deal with the fact that the pictures are being taken as the satellite is rotating. Okay, so that's pretty much the story on the satellite. Well, up to this point. The orbit is a very unusual orbit. It wasn't intended to be quite like this, but the orbit is a 53-degree orbit. It gets very close to this Jupiter, particularly at the equator, where it's about 2,500 miles away. And the plan is to do 33 flybys. Each flyby is 53 days. It was originally supposed to be 14 days, but something went wrong. And rather than try to fix that and potentially bollocks the whole thing up, they just left it in this rather long orbit. And each of the 33 passes by Jupiter covers a different portion of the planet. So by the time 33 are done, it is now into Perhovi, what it's called. They call them. Is now up to 18 or 28, excuse me. And the mission is planned to continue up through mid-year, a year from now. Okay, next slide is going to talk now a little bit about, oh yeah, this is actually a flyby of the planet. It looks like a video, but it isn't. It's a series of stills that have been put together to resemble a video. But the orbit around the planet is very unusual, and as part of its mission is to study the polar regions, and the polar regions have never been seen before. So we're going to get a view of it right here. So this is the South Polar region that it's flying over right here. So the orbits go over the poles. Each Perhovi goes over both poles and sweeps by very close to the middle of the planet. It's constantly changing its distance from the planet as it's moving over the planet. So these are all pictures that were taken. The raw pictures were taken by the Juno cam. The actual pictures are done by amateurs. NASA doesn't do these pictures. And I'm one of the amateurs that's doing this. But this is the problem. The field of view of even from the South Pole is never the whole thing. And so to get a picture like was, well, I'll show you in a second, it's not trivial. Okay, so we're done with that. Nope, I did something I shouldn't have done. I got to go back and share my screen again. Sorry about that. Okay. And now I need to get back to the slideshow mode. Okay. Okay. All right, here we are. Okay, so talk a little bit about the mission. I've sort of covered this a little bit already, but the mission is to measure the composition of the planet, its gravity field, its gravitational field, and its magnetic field. It also is looking to try to figure out how the planet was formed, whether it has a rocky core, the depth of its winds, which is actually a big you'll see that we've learned a lot from that, but the winds on the surface can be extremely large, up to 380 miles an hour. This is a view of the South Polar region, and I think I can, and this is without the words on it. So this is a composite of 3 Juno cam images taken on 3 different orbits, the first orbit, the third, and the fourth. And the reason that was necessary is the field of view was not big enough on each one of them. But when you put all 3 together, you can actually see the entire south pole of the planet. And that's pretty much what this is. So it was a difficult job to match and merge the three pictures, because there wasn't a tremendous amount of overlap between them. And each orbit was a little bit different, or there's small changes that are on the planet, so you can't use automated software to do this. It has to kind of done by hand. These, we'll talk some more about the South Pole, and these are cyclones, which are about 6,000 miles in diameter. Okay, let's talk a little bit about the actual structure of the planet, and that's is one of the goals. Now, this chart was not done by this, did not come from this particular mission. It came from really the Galileo mission, which managed to measure the what was going on in the clouds down to about 130 kilometers below, and there below the quote-unquote surface. Now, there is no surface to Jupiter. There is no distinct surface. It's gas, and it becomes gradually morphs into a liquid interior. But for purposes of identification, they tend to think of the surface as the one bar point in the planet's atmosphere, and that's what this is showing right here. And so the upper part of the atmosphere is largely gases and ice, ammonia hydrosulfide ice, and water ice. In fact, I just read an article today about this, and the water ice is about 1/4% of the atmosphere, which is actually a lot, more than people had realized. And gradually it transitions from all of this into hydrogen and helium. Now, I should say what the basic planet is mostly made up of hydrogen and helium. So it's likely a failed star, a star that did not get, was not quite big enough to start a nuclear reaction. But it's the fact that it's mostly hydrogen and helium tells you that it was starting out as a star, so to speak. And the gas, it starts out as gaseous hydrogen, but at around 12 bar, around down here, hydrogen goes through a phase transition, and it becomes a super fluid, which is a combination of liquid and gas phases. Now, the next chart, we'll go a little deeper in what's going on. So the deep atmosphere, which we were just looking at, is just this top little layer here. The next atmosphere is what's called the weakly conducting layer, which is largely hydrogen, but it has a lot of particulate matter in it that's been accumulated over the years. Then it morphs into what's called the highly conducting layer, which is still mostly molecular hydrogen, but there's enough ionized hydrogen, so there are some protons and electrons floating around here. So it's considered highly conducting. And then we'll get in the next graph, we'll get into the lower part. So I'll move on and talk to that when I get there. So the bulk of the planet is made up of what's called the metallic mantle, which is this section right here. There's helium, which it has, because of just the nature of it and the super pressures here, helium is condensed into clouds that are estimated to be about at this level. And this is the bulk of the planet, this metallic mantle, which is the metallic hydrogen. The inner core are where the heavier elements are, and it's still a debate as to whether there might be a solid core in Jupiter, but the current betting is there is not. Now you can see here's the Earth's radius down here, so Earth is quite small compared to the size of Jupiter. Now, getting into the science of Juno. So Juno, one of its goals was to measure these layers as deep as possible. So this was done by Juno's microwave radiometer, and it uses 6 different frequencies. As the frequencies wavelengths get longer, it can probe deeper, as you can see down below 200 kilometers and lower. And you can see with the pressure builds up rather rapidly down to 1,000 bar, 1,000 times the pressure on the surface of the Earth. Now, what came out of this? Well, they had a pretty good. They were able to identify exactly what some of these elements are. We have ammonia cloud, ammonia hydrosulfide cloud, water cloud, and then as it went deeper, there's some significant changes, and this is shown in this little piece here. But the next view graph, the next chart, shows this in more detail. One of the big surprises was this. There's a plume of ammonia right at this is the equator, so this is being plotted as a function of latitude, and so we have this very dense ammonia layer that's down at high pressure, down at the 100 bar level. But as near the equator, there's an upwelling of the ammonia to the surface, and then it spreads out. And so the theory is that ammonia on Jupiter is playing the role that water vapor does on Earth in terms of shaping its weather. But this whole story about understanding that this plume exists and has never been known before until this particular mission, because it was Juno's ability to use this microwave instrument to do this. That was the key. Okay, moving on. We'll talk a little bit more about the structure in a bit, but we'll look at the planet now. And this is another of the pictures that I took, or I didn't take. I took, in a sense, I took the data, the raw data from Juno, and made this picture. Now, this one was extremely difficult to do because it was 4 separate pictures that were taken on the same orbit. I think it was the 18th orbit around the planet. And the difficulty was that the satellite gets within 2,500 miles at the equator, which is up here. We're actually, I should say that this is a view of the sort of southern temperate zone. So here's the great red spot is below the equator. And so this is a view of the southern temperate zone looking at about 38 degrees south. But each of the pictures was taken at a much different altitude, which means it has a much different field of view. So we were very close at the equator, and then ultimately we were something like 40,000 kilometers away as we got further down. And so piecing these together, again, making a mosaic of these pictures where each one is a big difference in size from the other was not easy. But anyway, here it is. You see the familiar patterns that we've seen before, but we've never seen a picture that's that captures the South Pole as well as the zones and belts. Now, so just a little bit of nomenclature. The dark bands are called belts, and the bright bands are called zones. The zones are cooler than the belts, and they represent areas where there is a upwelling, and the belts, which are the darker areas, represent an area of downwelling. And so you have areas where gas and material is flowing up in the belts, in the zones, and down in the belts. And in between these, there are huge winds that are occurring because of that. Okay, the other feature of this picture, you'll see, I'll show you some more that are in a little more, that zoom in on this, is just unprecedented level of detail. Now, I think I mentioned that the Juno cam only is 2,000 pixels, so but it's so much closer than of course than the Hubble. So the images that we're seeing here are much more detailed than has ever been seen before. Yeah, I should mention that the Coriolis force, which is the deflection due when you have a planet that's spinning, which has a strong gravity field, there's a force that drives the atmosphere away from the equator, and that process is what causes these various zones and belts to form. The exact nature of the chemicals that are in these clouds are not known in detail, but it's thought to be a mix, certainly of ammonia, but of sulfur, phosphorus, and carbon that are mixed in with that. Okay, so moving on. Okay, so this is just the same picture, but all by itself. As I mentioned, it was 4 images. It was taken, I think, on the 12th of February in 2019, and it varied in distance from 10,800 to 42,000 miles. Each picture did. Okay, so this is interesting too. This is going way back to the Voyager satellite in 1979. So, this gives us a unique view here of the circulation on the planet. And so this is a sequence of stills again, but made into a video. So here you can see the motion of the, I can play it again. It's a short little spiel. It's a motion. So you can see the zones traveling west to east, and the great red spot, which is down here. You'll notice it is counterclockwise. It's going counterclockwise, and it's called an anticyclone, which is equivalent to a high pressure area on Earth. Okay, this chart shows the winds that occur on Jupiter, and so we have a picture of the planet, and these are the winds. And as I mentioned briefly, in between the zones and the belts, there are what are called jets, and the eastward progression that we are seeing with the zones are going east, and between them and the zones, the belts that are going the other way, there's a jet. And these jets speeds can be as much as 380 miles an hour. This shows a graph of the speeds, and you can see they peak out and in the mid-temperate areas, both in the north, above the equator, and below the equator. So it's indicative of an awful lot of activity on the planet. So there's a wide variety of, and we'll talk some more about that, of activity on the planet that's driven partly by the speed of these storms and these belts and zones whipping around the planet at these incredible rates. Okay, so the next chart is going to look at the gravity field. So this is so we have the same picture, but now what we're plotting on here is the gravitational asymmetry of Jupiter that was measured by the Juno satellite. And it's interesting how they do that. What's going on is that the fact that the gravity is varying makes the motion of the satellite change, and there are two transmitters on the satellite that beam back constantly the Doppler shift associated with this motion to Earth. And using modeling and taking this raw data, scientists are able to figure out that the gravitational field is going through these incredible variations from north to south. Now, this asymmetry also, you can see it reaches its biggest point at this mid-northern latitude of about 24 degrees. But it's also a telltale sign of that also is the wind. So these are the wind gradients. It's not the wind itself. It's the difference. It's the gradient in the wind, the rate of change of the wind. And you can see that associated with these large changes, asymmetries in the gravity, there are asymmetries in the wind gradient. The wind directions are changing extremely fast. And it's all related. The fact that the gravitational field is varying is definitely related to the fact that the winds are changing. So it's a signature of these wind changes, wind speed changes, as well as flows that are occurring below the surface of the planet. Okay, I think that's yeah, and yeah. So all this is I just plotted the two charts on the same in the same page. So this is the wind speed, and this is the gravity anomaly, and the wind speeds and the wind gradients here and here. Okay. The next chart is a blow up of the picture I showed earlier that showed the whole planet, but it shows in more detail what's going on in the surface. And the surface has a tremendous amount of activity going on it, both with this motion of the belts and zones, but also a large number of cyclones and anticyclones. So you can see these incredible patterns that exist on the surface, having to do with the surface activity of the atmosphere, and a lot of these represent just huge storms. Now, one of the keys one of the goals of the mission was to determine how far down do these winds go in the planet. That's never been known. And so they've, by using the information from the gravity measurements, they've been able to infer how deep the wind speeds are going. And the next chart, I think, is going to get into that. Yes. Okay, so this is a plot at the equator as a function of depth along here. And this is the dense decay profile of the wind speed, or the speed of the, which at some point, it's the motion of the atmosphere. At some point, it becomes even a liquid. But what's remarkable is they've inferred the fact that at the equator, that this motion goes down to 4,000 kilometers below the surface. And they were able to determine that from the gravitational measurements. Now this lower plot, and by the way, the blue, the shading, the light blue is the uncertainty in the measurement. This plot shows the same information, but as a function of latitude. So here we have the equator, and then we have the northern latitudes and the southern latitudes. And you can see that this the wind speed varies. The depth of this, which is 4,000, very deep at the equator, is much less at the polar region. So it goes from quite deep to much less on each of the poles. So again, this is one of the chief scientific results of the mission, which is still going on, by the way. Okay. We're now going to talk about the, okay, well, here's, this was, this is another video, a pseudo video that'll show the pattern of motion, not just on the surface, but down below the surface. And it's, I'll play it, and then we'll talk a little about it. So you can see the zones here and the belts in the opposite direction of motion. But then this is the deeper, so you can, the motion, so they are inferring from the data that I just showed that this motion continues down below the surface, going down thousands of kilometers. But below about 4,000 kilometers, there is motion, but it's moving as a solid body. There isn't this differential motion that we see in the outer 4,000 kilometers. And one of the surprises that came out of the data is that a measurement or an estimate of the total mass involved with the motion of these streams, these outer layers, and it represents about 1% of Jupiter's mass. Whereas in contrast, Earth's atmosphere is less than 1/millionth of the total mass of the Earth. So a significant fraction, only 1%, but much larger than an Earth, of the mass of the planet is involved in these in this outer atmospheric motion, which extends quite deep into the planet. Again, realizing that there is no solid part of the planet; it just transitions gradually from a gaseous environment into a liquid environment. Okay, so talk a little bit about the storms on the planet. So here is another one of my pictures. This was taken on Perhovy 20, the 20th orbit around the planet, from 3 different images on an average distance of about 10,000 kilometers. And this is now taken at 39 degrees north. So this is in the northern temperate zone of the planet. Yeah, and so this picture is a crop of actually of one of my other pictures, but it shows in a little more detail one of these really stormy, convoluted areas where the belts and zones are all twisted up into this gigantic, what has to be a gigantic storm. But you can see these cyclones and anticyclones. These are the circular areas. But in addition to that, there's all of this convoluted flows that exist. And this almost looks like a modern painting rather than actually a picture of what's called an actual photograph of the planet Jupiter. This is interesting to me. This looks like a creature here. If you look carefully, you'll see 2 eyes here, maybe a mouth, and then there are some arms here that are holding these 2 things, and then these long legs that extend down here. So I kind of identified that. This looks like a coiled snake at this point, but it's pretty amazing. So there are lots and lots. Well, you can see from the pictures that there's lots and lots of these vortices, and there are 2 types, just like on Earth. There's cyclones and anticyclones. The cyclones on Earth are the storms. The anticyclones are the high pressure areas. But what's unusual on Jupiter is that 90% of the large ones are anticyclones, which is not the case on Earth at all. Essentially the high pressure, so the high pressure areas, so to speak, are the dominant here. They're mostly white, with the giant exception of the Great Red Spot, which is red, but it's also an anticyclone. Okay, so this this is actually a part of the picture that I showed earlier of the lower part of the planet, but I'm just showing the upper part. This actually represents just 2 of the 4 pictures that I was referring to, but you can see the detail in the Great Red Spot here very nicely, and then the detail in these zones and belts. The next picture is even more detail of the Great Red Spot. It rotates counterclockwise at about a speed of 250 miles an hour, with a period of about 6 Earth days or 14 Jupiter days. Remember, Jupiter day is 10 hours, so it's very short. This spot is getting smaller. In the 1800s, over 100, maybe 50 years ago, 30 years ago, it was probably twice the size that it is now. It is shrinking. Right now, it's just a little bit larger than the size of the Earth, 1.3 size, but it was once several times, 3 times the size of the Earth. This and it's getting smaller, so the thinking is that it might actually disappear in maybe semi-short order, maybe in the next 20 to 30 years. Now, one question is why does a storm even last this long? I mean, this is hundreds of years now, maybe, that this thing has left, because there is no surface. Since there is no surface storms on Earth, the drag from the winds at the surface slow the storm down and cause them eventually to peter out. Well, there is no surface in Jupiter, so these storms last a long, long time. Okay, so now turning to the South Polar region. So here we have the picture that I was describing briefly earlier. It's 3 separate pictures, 3 separate orbits. This is, so we're into a very different look to the planet from the belts and zones in the middle latitudes. And what we have here are a series of cyclones at the poles. And on the South Pole, there are 5 cyclones surrounding a central cyclone. And I should mention, this picture has actually won an award. I submitted it to a Wikimedia science contest, and it was judged as one of the 5 best science pictures in the year. And it's now been submitted to an international competition. My picture of the eclipse, which is actually over my shoulder here, also won a similar award in 2017, one of the top 5. And it was a finalist in the international competition. Okay, so now we're going to look to the North Polar region. So this is a infrared image. The colors indicate the temperatures. The yellow color is actually quite warm. It's about 9 degrees Fahrenheit. But then as you get into the red colors, it gets into minus 180 degrees Fahrenheit. You can see that there's an octant. There's 8 separate cyclones on the north. Now this is a composite. This is the North Polar region with a picture, a visual picture over here that has the same orientation as this does. So you can see that these cyclones stand out much more in the infrared than they do in the color. But you can also see what I was saying earlier about the difficulty. This is the size of any one of the pictures that I had to get to do the composite to show the entire pole. One of the amazing things, and that's probably the only reason that I could have done a picture, or anyone could do a picture, well, these pictures are taken during one pass, the IR picture. The actual pictures, the visual pictures, are taken over many passes. But what's amazing is that these patterns don't change very much between these orbits, because these orbits are 53 days each. And remember, I said that this picture on the South Pole was 3 different orbits, from the 1st, 3rd, and 7th, and 4th. And for it to have any pattern, it means that it really didn't change very much over a period of several hundred days. And that's also a surprise and a bit of a puzzle. Yeah, and so one of the other interesting features of Jupiter is lightning. Jupiter has lightning. Now, it doesn't have lightning like it does on Earth. Jupiter's lightning occurs in the poles, whereas in the Earth, it occurs in the temperate regions, in the equatorial regions. And one of the thinking about this is that on Earth, the Earth gets a tremendous amount more heat from the sun, and it's the heat that's interacting with the clouds that causes the turbulence in the storms. Whereas on Jupiter, the thinking is that the much less sunlight is actually stabilizing the atmosphere in the equatorial regions, and it is, of course, getting no sunlight almost at the poles. And the thinking is that's why. And then so the storms in these cyclones in the polar areas are generating the lightning. We move on to the magnetosphere. Jupiter has an amazingly strong magnetic field. It's the surface field is 20 times as strong as the surface field on Earth. And the magnetosphere, that is the sum of the energy in the magnetic field, is 20,000 times greater amount of energy in the magnetosphere surrounding Jupiter than on the Earth. And this magnetic field is generated by the motion of the spinning motion of the planet and the motion of the in the conducting areas, producing this plasma, producing a very strong electric current that is producing the actual magnetic field. So what you're seeing here is the front part of the magnetosphere interacting with the solar wind, and it produces a bow wave. But then the trailing part of it extends quite a ways away, all the way, in fact, to the orbit of Jupiter, of Saturn. In addition to the fact that there's this large magnetic field, there's a plasma of charged particles that are surrounding the planet as well. So one of the challenges for the satellite, the Juno satellite, was to survive in this plasma. And the plasma occurs because the moon of Jupiter, Io, is a volcanically active planet, and it's quite close to the planet and is spewing charged particles out around that surround the planet. And the planet, then the magnetic field from the planet produces this torus, this plasma torus, which is a highly energetic field of electrons and protons and other charged particles. So now this is just a picture of Io. Io is very active volcanically, and the energy, that the heat that is generating the volcanic activity, all comes from the tidal forces that are affecting the planet. And this is true for all of the Jupiter inner moons. The field, the gravitational field from Jupiter is so strong that it changes dramatically over the width of the planet. And because of that, there's a lot of heating that's going on because of the difference in the gravitational field. And that heating is what's responsible for the volcanic activity on Io. We're getting towards the end. This is a map of the magnetic field as a function of longitude in this direction and latitude. So this is all the way up to almost to the polar regions. But you can see it just varies tremendously, and it's generated. I was fumbling for the word, but it's generated what's called the dynamo, the motion of charged particles in the magnetic caused by the spinning of the planet. Is this current is called a magnetic dynamo, and it's the field from this electric dynamo that's creating the magnetic field. Next picture actually will show, this shows the magnetic field variation in the north and the south pole. And this is another little video that'll show the field lines, the magnetic field lines, and you can see that there is quite a jumble. They're not as neat as they are on the Earth, where they begin at the North Pole and end at the South Pole. Some of these field lines begin randomly right through the entire planet. Okay, the last topic is the aurora. Guess what? Jupiter has an aurora. This is actually a picture of the Hubble image and showing the aurora. But the aurora is the source of the aurora is extremely different than ours on Earth. Earth, we get charged particles from the sun, which interact with the magnetic field on the Earth, and the charged particles ionize the atmosphere. The solar particles ionize the atmosphere, and we get a discharge that results in our northern lights. On Jupiter, it has a permanent aurora, and the charged particles don't come from ionization from the sun. They come from the particles, again, guess what, from the Galilean moon Io, which is spewing all these charged particles at Jupiter. And the interaction of those charged particles with the magnetic field causes them to ionize and produce light. And that's what the aurora is. So it's a permanent aurora, unlike that occurs on Earth. And I could give a whole talk on the moons. I'm not going to, but these are the 4 Galilean moons. Just briefly, there are 79 moons around Jupiter. At the time when this graphic was written, it was thought that Jupiter had the most moons, but it now appears that Saturn actually has more. But Jupiter's moons, of the 79, there are 8 of them. There are regular satellites. 4 are the Galilean satellites, which have regular orbits that are prograde that rotate around the planet in the same direction the planet is rotating in nearly circular orbits. The rest of them are just a conglomeration of irregular prograde, retrograde orbits that are very irregular. And I think that's it for the talk itself. I'm going to show you a few pictures in a bit, but all of the pictures, all of the images that from the Juno mission, in particular the scientific data, but also the pictures that the raw images for the from the Juno cam are all online, and there are more of them. I stopped doing this about 6 or 7 months ago. So, but there are new pictures. One of the concerns was, though, that the camera might be because of the plasma around the planet, the camera might be degrading, but it still seems to be going. And that's it. So, but so I thought I would show you some pictures from my observatory here in Jackson. I have 3 telescopes. I have a 20-inch plane wave. I have a 12-inch plane wave, and I have a 6-inch refractor, a Takahashi 6-inch refractor. This is an image that I just finished. I haven't posted it yet. It's of M16, the Eagle Nebula. And this is 68 hours of imaging. This is a narrowband image. And I've been taking pictures of the Eagle Nebula probably for 8 or 9 years. But this year I added 40 more hours. My goal was to be able to get more detail in the Pillars of Creation area. And if you look at this next picture, this is my picture that I just I cropped and zoomed. This is the Hubble, the latest of the Hubble Pillars of Creation images. And there's no question the Hubble image is sharper than mine, but most of the detail that is in the Hubble image is also present in my image. And so I was quite pleased that I was able to get something that even comes close to looking at, because as you look, you see these patterns, the same patterns here. You look at the patterns here, there are same patterns here. The patterns up in this arm, and all the detail that down in this area are all identical to what the Hubble has produced. It's just not quite as sharp. But anyway, for a 20-inch telescope that's terrestrial based, I don't think that's too bad. But what it took was 68 hours of imaging, because I used some fairly sophisticated tools to bring out the detail. And you can only do that if you have a super low noise image. If you have any noise in the image, all you do when you're trying to bring out that high level of detail is you make more noise. And so I used some very sophisticated tools to bring out the detail in my image, which does, I think, a pretty amazing job in comparison to the Hubble image. This is another one of my images. Now, this is one I've taken a couple of years ago, but I've actually I've using some of the same tools. I went back and reprocessed this. This is M51, Whirlpool Galaxy. And so here's my image on the right. Now, you'll have to pardon the difference in color, but this picture was taken from the 200-inch Palomar telescope on Mount Palomar in California, 200 inches compared to 20 inches. And again, just like the Hubble image, my image isn't quite as sharp, but most of the detail that's in this, even down to the patterns of stars, group of 4 stars here, is just not quite as sharp, but is pretty much showing the same level of detail that you're seeing in this Mount Palomar image. Again, I was impressed. I'm using some secret sauce in this one too, just like I did on the Eagle Nebula. Now here's a few more. You all have, I'm sure, are astronomers who have looked visually at the at M57, and it's a planetary nebula, but you've probably never seen an image of M57 that looks like this. And what this is a 70-hour image that I just completed of M57. And what you normally see is just the center area here, and you can see the small the star, the white dwarf at the middle. That's the remnant of the original star that formed this. But there are these very interesting patterns that go way beyond the central area into several. This is a narrowband image, and red is hydrogen, blue is oxygen, and there's the sulfur is green, so this outer area has a certain amount of sulfur gas. There's also this cute little galaxy up here that's I have no idea how far away it is, but it's probably thousands, hundreds of millions of light years away. Here's another image that I just took. This is of in the Virgo constellation, and it's called a galaxy trio. So these are 3 interacting galaxies in the Virgo Virgo constellation, but also in the Virgo, the giant Virgo galaxy cluster. But these 3 are quite close to each other, and they're interacting. They're all being stretched and pulled, and they will eventually all merge into a single galaxy. But this, I think, is NGC 5566. But it's called the Galaxy Trio in Virgo. This is an image that I just finished. This was not taken with my telescope. It was taken, the raw images came from a telescope in Chile. This is of what's called the Statue of Liberty Nebula, and for obvious reasons. It's in the Carina constellation, about 58 degrees south. So this is not something we in the north can see at all. But I've been able to get the data from this telescope, and I've been processing a number of pictures from it. And so this is my version of the Statue of Liberty. This is another image from from Chile. This is M83, Messier 83, which is called the Southern Pinwheel, which is just fantastically beautiful. These were taken by a 17-inch telescope, a CDK 17, Planewave 17, right in between mine too, which is the 20 and the 12. And I think that's it for the night.
Great, Mike. Thank you so much. That was fascinating and beautiful images too. Why don't we take some questions from our audience? If anybody has anything they'd like to ask, you can unmute yourself at this point and ask directly of the question of Mike. This is always a little bit dicey because if we have too many people unmute simultaneously, but I see a couple there. Meg Thatcher, you seem to be unmuted.
Yes, so uncharacteristic. Michael, first of all, I'm so impressed by those photos. It's amazing. I'm just really, really obviously speechless. A quick question about the Juno mission. You say it's going to be ending within the year. Do you know if there are plans for an extended mission?
Well, it's already in an extended mission, as it turns out. But I think it could continue. Whether they will or not is another question. If they don't, they'll do what they did to the Cassini and plow it into the planet. But it's at least going to go on. It's, as I said, it's on its 28th orbit, so it has 5 more orbits in its nominal plan, and I think that does take it into the middle of the next year. So at that point, I think it's not clear what's going to happen, but it's at least going to go that long.
I should mention Meg is our featured speaker next week with the Marvelous Moon. So as
Okay.
a preview, I'll send you a link, or I'll put a link in our chat area.
Sure.
Michael Gettings, I see, is unmuted. Mike?
Like, say there's like a storm on like Earth, would that affect Jupiter, or like would it affect a planet?
No, it wouldn't. Jupiter and the Earth are quite far apart, so there's nothing we do on Earth is going to affect Jupiter. I can't necessarily say the same thing in the other way, but yes, I can. Nothing is going on in Jupiter, but Jupiter is had an awful lot to do with the formation of our solar system, and we're here partly because of Jupiter, because Jupiter acted like a big vacuum cleaner and swept up an awful lot of the early debris from the inner solar system and allowed Earth to have really long periods before cataclysmic events occurred, like asteroids hitting the Earth. And the fact that we've had so few of them is partly due to the fact that we have this giant planet out there that has scooped up a lot of the debris that otherwise might have endangered Earth.
Okay. Great question. Great question.
Thank you.
While we're waiting for somebody else to unmute, I'm going to post a link right now. As I mentioned earlier, we're in the middle of a capital campaign. If you're interested in a donation, please visit that link on Bloomerang. And here is my private personal information, my email address and private phone number. If you might be interested in a more significant contribution to our Astro Science Center, please give me a call. I would love to talk to you. If not you, maybe you know somebody who would be interested in something towards our Astro Science Center. We'd certainly welcome that at any time. And finally, here's a couple of links to our website, our Facebook page, and our YouTube channel, which will host this. I'll post this recording of tonight's presentation tomorrow morning. Take a little break if there's other questions before I provide just a last couple of details.
I might just add a comment or two about if anyone, I do have a website, by the way, so my pictures are visible on my website, and I should have written it on the last view graph, but it's pretty easy. It's earthandskyimaging.com, earthandskyimaging.com, all run together.com. The other thing is, if you're interested in purchasing any pictures, I generally refer people to Wyoming Stargazing, because Wyoming Stargazing is a not-for-profit, just like Adirondack Sky Center. And Wyoming Stargazing, I donate my pictures to them, and so you can purchase pictures from on their website. And again, if you just Google Wyoming Stargazing, you can get to that webpage as well.
I'll try to remember to put a link when I put the video up. I can put a link to that in the comment area.
Seth, can I ask you a question?
You bet.
Michael, I want to thank you for a beautiful presentation. Could you talk a bit about the technical process of creating these photos?
You're talking about my photos, or well, the two are very different. You mean the photos that I did on the Jupiter satellite pictures?
Yes, some of the images you showed us this evening where you talked about merging various images and
right. Okay. Yeah. All of that was done remarkably well. It was all done in Photoshop. The simple answer is all done in Photoshop. But so what I had to do was I had to take the raw images, which are all different shapes. They come in little half moon, quarter moon shaped slices of the planet, because that's the pattern that the actual camera or that the satellite makes as it's passing over the planet, and merge these into a single image. And as I mentioned, the pole in one way was easy and it was hard, but it was easier because they were all pretty much taken, the three were all pretty much taken from the same altitude above the pole, about 90,000 kilometers. But the key there was matching up the detail, and you can't just go in and use, like if you're taking terrestrial pictures and you want to take a mosaic that is, 3 or 4 pictures and then merge them into a panorama. The scenery doesn't change between the pictures, so you have an overlap between them, and the software will recognize the common areas and merge it all automatically for you. That doesn't work for this because the patterns change subtly because they are separate different orbits, and so there are small changes that occur in between, in these 53-degree, so it was over 200 days. 200 days associated with those different periods. So that was all done by hand. I just had to merge, adjust and merge and squeeze and pull to get those. And then that was even made more difficult on the other picture that I showed, where I showed the one that shows the southern equatorial, southern temperate region of the whole planet. That was 4 pictures, and again, that was all hand. I had to rescale those pictures and distort them because even on a single picture, the elevation was changing, and so it was a lot of squeezing and tugging to make it all into a single picture. So the answer is, lots of layer work in Photoshop, lots of hand manipulation to make the features all line up and produce something that I think is pretty close to what is really there.
I should mention that this year is an exception due to COVID-19, but the Adirondack Sky Center each year does an astrophotography conference that is very hands-on and specializing in capturing and then processing in computer labs with the Photoshop, PixInsight, and all of that software. So if you're interested in that side of things, keep your eyes open or keep a lookout for that in 2021. I see. Yep. Stuart.
Yeah, interestingly enough, I was going to offer such a course here in Jackson this year, but it is not happening for the same reason. But I was going to do that. We would go out and use Wyoming stargazing telescopes, take pictures, and then process them.
Yeah. Sue Stewart has her hand raised.
Yeah, I do.
2 questions, Michael. First of all, why is the rotation of Jupiter so fast? And the second is, why are some of the moons the Galilean moons are in a regular orbit and the other more numerous moons are in irregular orbits? Were they captured later?
Yeah, okay, that's a good question. In fact, there's an article I was just reading today I think it was in Science Magazine, current issue. No, it was I'm forgetting astronomy. But anyway, it talked about the formation of the Galilean moons. And the regular moons, including the 4 Galilean moons, were all formed during the original formation of the planet itself. And so it was a part of the formation of the planet where the debris that was in the solar system at the time that the sun was forming. I mean, all the planets are the leftover debris from what was left over when the sun formed. And so Jupiter ended up as accumulating a lot of this debris, and the Galilean moons are thought to have formed just about at the same time as Jupiter was forming. But a lot of the other moons, the irregular moons that have that are out of the plane and rotating in different directions, are probably captured material. You remember I was talking about during the after the major planets were formed, there was still a lot of activity in this solar system early on in the first hundreds of millions of years. And Jupiter was capturing an awful lot of that junk that was flying around. And a lot of that junk coalesced into these other into these other moons. And the same could be true for a lot of the irregular moons around Saturn as well, by the way. Saturn has a regular series of moons, somewhat like Jupiter, but it also has a lot of irregular moons. And they were thought to have formed in this way by capturing material over after the initial formation of the planet. Now, to answer your other question about the rotation, I don't know, but it obviously had to do with the process of the original formation of Jupiter that caused the spin that is occurring, and also original formation of the sun. And so with Jupiter being as big as it is, there had to be the actual process of forming the sun and the largest planets. There's a lot of spinning and that's going on in the solar system. And of course, we know that they're spinning because that's the reason why the planets are located in a plane, because that spinning motion of all that material produces tends to produce a planar surface or planar area where the planets are orbiting. And so some of that spinning motion around the sun gets captured in spinning motion of the planet itself that's being formed. So it goes all the way back to the formation. But it's a good question, and there are probably people who have thought about it and have a better answer. I think my answer is probably correct as far as it goes, but there's probably more detail that's available if you dig into it.
We have a question from a very patient young man, looks like Jeffrey Cook or Koch. I'll ask him to unmute himself and ask his question.
So can it like if an asteroid or meteor, can it like hit something and then bounce off? Like,
well,
like,
yeah, well, asteroids are out there, and they are in fact hitting things. Jupiter had an asteroid hit it just I think last year or a couple of years ago, and it was and it was observed. The actual impact of an asteroid hitting the surface of Jupiter was observed. So this does happen. And in fact, asteroids hit the Earth all the time, small ones. Most of them never reach the surface, they burn up. But a couple of years ago, an asteroid did hit the surface of the Earth in Russia and created a fair amount of damage. It could have been a lot worse, but it was a glancing blow. And that's something that unfortunately we all have to, that's back in the back part of our minds. There's always a possibility that there's an asteroid out there lurking that can in fact potentially hit the Earth. But scientists and astronomers keep a pretty good eye on these things, and we're pretty sure there isn't one coming anytime soon.
Well, that's good to hear, Mike. Throughout things,
is it possible that the irregular moons around Jupiter are in flux? Like we have an irregular moon right now, if I'm not mistaken, around Earth, a second tiny one.
yeah.
But they say it's going to get slingshotted off at some point. Is it possible that some of those other ones are going to?
It's possible. It's possible. You know, they're still actually discovering moons on Jupiter and Saturn because you know it's a long way away, and some of them are quite small. Yeah, but you know, as I mentioned, Jupiter and Saturn get close to each other, or their orbits line up. For every 5 orbits of Jupiter, Saturn and Jupiter line up. They're in a resonance. Just that interaction could cause some of the moons to change their position and possibly you know, leave, as you were speculating.
Thank you.
I just want to mention that I just posted to the chat area, Meg Thatcher's talk next week, Our Marvelous Moon, with a registration link for being here today. You get early registration opportunity. The link will be made available to the public on Monday. However, I want to mention that we're encouraging kids to join this one next Friday. This is the one, the first of two that we have planned that do not require a high school diploma or any experience in high school science necessarily to take part in. However, it will be appropriate for all ages, and as everything else, you can always come home with a nugget from them all. So unless there's any other questions, anybody else out there want to ask?
Yeah, I'd like to ask about gravity.
Yeah.
Go ahead, sir.
Okay, I'll make a quick comment. Michael, I belong to a ham radio club out here, and as such, most of the guys are into solar weather, et cetera, et cetera. So I happen to send your pictures around of the Statue of Liberty that you took, and they were amazed at your photography. So I just wanted to compliment you on the work you do, because it's unbelievable. So
no, thank you.
I'll get out of here. I just wanted to mention that.
Thank you.
Thanks, Al. Anybody else? Last question of the evening.
Was there a gravity question?
Yeah, if I may.
Yes.
All right. I felt like one of the big takeaways from the Juno mission was that there's kind of a tremendous amount of mass just sloshing around on Jupiter, and that you've got this tremendous variation in gravity with latitude.
Yes, absolutely.
I'm wondering if be they artificial or natural.
If what's artificial?
Well, if the orbit of the satellite and the orbit of the natural satellites around Jupiter is affected by that variation in gravity.
Oh yeah, absolutely. It has to be, I would think, particularly the inner ones, because the gravity of Jupiter is extremely strong. Obviously, it's so huge, and Io is producing all this volcanic activity because of the that gravitational field that's heating it up internally. And yeah, as it's passing around the planet, it's got to feel the variation in the gravitational field that's occurring, and its motion must be affected, just like the motion of the Juno satellite is affected by that variation in gravity. That's how, as I mentioned earlier, that's how they're measuring the change, the gravitational field. They're actually measuring its effect on the satellite's motion. And so you would think that that would apply to certainly the near-in moons. Yeah, and needless to say, their moon, that's the other interesting point. Actually, it's all interactive too, because the motion of those moons is affecting the gravity on the gravitational field on the planet in particular. I mean, it does look at what happens to our tides. So those planets have got to have an effect on Jupiter, just like Jupiter's having an effect on them. It's got to be both ways. Yeah.
Right. Again, Mike, thank you so much. What a fantastic evening, full of great information and stunning photography. So thank you so much for being here. If we can get a virtual applause going, I'm not sure how to do that exactly, but I certainly would encourage it. So thank you very much, and thank you everybody for being here tonight.
Sign up. I see some hands clapping. So that's right. Thank you.
All right, good night, everybody. We'll see you next week for The Marvelous Moon.
Good night.
All right. Thank you. All right. Good night.